Hey, everybody. You've probably seen a lot of mathematical statements. They say something like, for all x, blah, 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 or there exists a y, blah, 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 blah. How does that language, the for all and there exist, interface with the stuff that we've been talking about propositions so far? We'll be talking about that today when we talk about quantifiers. In mathematics, we typically use two quantifiers. The first is the existential quantifier, and it is typically written in English as there exists x with some property, or there is an x with some property, or maybe there is at least one x such that. We represent this compactly by this particular symbol. For the record, I have to admit it took me a few years to figure out where this symbol comes from, and no one ever told me. More on that in a second. The second quantifier is the universal quantifier, typically written in English as for every x or for all x, and is denoted by this symbol. Sometimes we don't even explicitly say it and it is understood, and this is something to watch out for. Okay, so where do these symbols come from? If you look at this, you'll see that the for all symbol is just an upside down A, and the exist symbol is just an upside down E. Here are a couple of examples. Number one, let's take the statement, there exists a number less than 1. This can be written using quantifiers in this way. Number two, every odd number squared is odd. We've also written this in earlier classes by n odd implies n squared odd. Note here that there really is a universal quantifier, and we should write the sentence this way. Now we add an idea to make our quantifiers even more powerful. Definition: a propositional function is a family of propositions that depend on one or more variables. The collection of allowed variables is known as the domain of the function. Here's a simple example. Let us define p of x to be the propositional function x cubed is less than 7, where we allow x to range over the real numbers. It's equivalent to think of a propositional function as a function from the domain to the set Tf, although you don't have to think about it that way. We might also write this in code, like in Python, as follows. Note that this function returns true or false based on that condition. Now we can put these two ideas together. If we have a propositional function and add a quantifier, or maybe even more than one quantifier, we call this a quantified proposition. So for all x, p of x is the proposition that p is true for every x in the domain, and there exists an x, p of x is the proposition that at least one x in the domain makes the function true. Recall our example, p of x is x cubed is less than 7. We can see that there exists an x, p of x is a true proposition. For example, p of 0 is true, therefore there is an x that makes this proposition true. However, we can also see that for all x, p of x is false. And another example is clearly p of 100 is false, so this thing does not hold for every x. Okay, so how do we negate a quantified proposition? Let's think this through. What is the negation of for all x, p of x? In English, we would say it is not true that p of x holds for all x. That means that p of x fails for some x, or there exists an x such that not p of x. Similarly, what is the negation of there exists an x, q of x? If we say that there does not exist an x in the domain such that q of x is true, this means that q of x must fail for every x in the domain. Or another way of saying that is for all x, not q of x. Basically, you can think of it this way. You can always slide a negation sign through a quantifier, but it flips the quantifier, exchanging the existential and universal quantifiers. Also, a note here. You might have heard the notion that it is easier to prove a theorem false than to prove it is true. And this is sort of true, but we need to be a bit careful. Here's a basic rule of thumb about proving quantified propositions. Proving for all x p of x tends to be hard because you need to show something holds for all x in a domain. But proving there exists x that q of x is true can be a lot easier, although of course this may depend on q. So since the negation of for all is there exists, when we have a quantified proposition with a universal quantifier, it tends to be easier to show it's false. This is because to show that for all x p of x is a false statement, we only need to show there exists x that not p of x is true. And basically we just need to find a single x in the domain that breaks the proposition and we are done. In general, this example is known as a counterexample to the original claim. For example, consider the statement for all x in the reals, x is greater than 1. This statement is false, and to show it is false, we just need a single x where it fails. So take 0. 0 is not bigger than 1. Therefore, the theorem fails. Another example is the statement for all integers n is even. But again, we can disprove that by giving one counterexample, and of course the number 1 is not even. So the precise statement is that it tends to be easier to show that there exists is true and for all is false. Conversely, it's hard to show that a for all is true or that a there exists is false. So in another sense, proving that something does not exist typically is harder than proving it does. Here's a more complicated example. Consider the quantified proposition, for all real x, there exists a real number y, such that for all real z, p of x, y, z is true. So how do we negate this? The rule is just this. We can slide the negation symbol from the outside to the inside, just making sure that every time we pass it through a quantifier, we are careful to flip the quantifier. And by flip, I mean exchange the two. There exists goes to for all, or for all goes to there exists. Thus, the negation can be computed this way. Finally, we get the answer. There is a real number x, such that for all real y, there exists a real number z, such that p of x, y, z is false. Okay, so now we can present an example of such a complicated quantifier that comes from real life, so to speak. Let's remind ourselves of the epsilon delta definition of continuity. You may have seen this in a calculus class at some point, and if you haven't seen it, you certainly will soon. So here's the definition. We say that the function f of x is continuous at x naught if, for any epsilon greater than 0, there exists a delta greater than 0, such that for any x with the absolute value of x minus x naught less than delta, we have the absolute value of f of x minus f of x naught less than epsilon. This can be written as the following proposition, with 3 quantifiers and 1 implication in the middle. Okay, now we want to write down the definition for a function to not be continuous at the point x naught, or as we call it, discontinuous at that point. Let's abstract this a bit with propositions and write this as the following sentence. For all epsilon greater than 0, there's a delta greater than 0. For all x greater than 0, p of delta x implies q of epsilon x. Now we can crank out this negation using 2 ideas. The first is that we can pass negations through quantifiers, as long as we remember to flip. And the second is that we can write p implies q as not p or q and apply one of De Morgan's laws. After a bunch of computation, we finally obtain the definition of discontinuous. There exists an epsilon greater than 0, such that for any delta greater than 0, there exists an x with x minus x naught less than delta and f of x minus f of x naught greater than epsilon. Which kind of vaguely in words says that no matter how close we get the input to our target input, we can't get the output close to our target output. Okay, one last comment. Order matters. When different quantifiers are in a particular order, we cannot in general exchange them. For example, the proposition for all integers n, there's an integer m such that m plus n equals 0 is true. One way to see that is, of course, if we just take m equals minus n, then minus n plus n is 0. In contrast, the proposition there is an integer m such that for all integers n, m plus n equals 0 is clearly false. However, when we have the same type of quantifier, we can exchange their order. For example, if we have the sentence for all x for all y p of xy, we can also write that as for all y for all x p of xy. One last complicated example, but I love this example because this is something that everyone is going to see in their future mathematical career. If you've already taken linear algebra, you've absolutely already seen this, and if you haven't yet, don't worry, you will. Okay? But if you haven't yet seen linear algebra, when I use the word vector, just think about vectors in R3, like we had in Calculus 3. Okay? If you have seen linear algebra, then I can be talking about a more abstract notion of vector. So here's a definition. Very powerful and important definition in linear algebra, and it goes like this. Let x, y, and z be vectors. We say that these vectors are linearly independent if for any real numbers a, b, c, if ax plus by plus cz equals the 0 vector, then a and b and c all had to be the number 0. If we write this out more in quantifier language, this says, for all real a, b, c, ax plus by plus cz equals the 0 vector implies a equals b equals c equals 0. So how do we negate this? Well, the calculation is very similar to what we did for continuity. Recall that we can pass the negations through the quantifiers, remembering to flip, and then also use De Morgan's law on the implication, and this becomes, there exists a, b, c real, such that ax plus by plus cz equals the 0 vector, but it is not true that a equals b equals c equals 0. Let's think about this. What is the negation of the equation a equals b equals c equals 0? It means that some of the numbers, a, b, or c, are non-zero. Not necessarily all of them, but at least some of them. So this is how we get the definition of linearly dependent. We say that x, y, and z are linearly dependent if there exists three numbers a, b, c, not all 0, that gives ax plus by plus cz equals 0. Okay, I love this example. When all of you go ahead and take the linear algebra course that you will soon, this is something that's going to come up, and I find when I teach that course, this negation is one of the things that students have the most trouble with. Okay, that's all for today.